This is the Optim Update. I'm Bogdan Christe, and today's guest is Jared O'Leary, CEO and co-founder of SirenOpt. SirenOpt is a deep tech company building what they call manufacturing intelligence, the ability to see what's actually happening to a material while it's being made in real time on the production line. If you've ever wondered why even the most advanced factories in the world still can't fully control their processes, this conversation is going to make that make sense. We talk about the physics, the commercial reality, and what it's actually going to take to build the autonomous factory. And without further ado, here's my conversation with Jared O'Leary. Mr. Jared, welcome. I'm excited to have you on, man. How are you feeling? Are you ready to talk about manufacturing intelligence, autonomous factories?
Yeah.
Awesome, man. Yeah, so let's start. You did say something to me that I keep coming back to. You said that manufacturers today are essentially more or less flying blind. I'm super curious, what did you mean by that?
Yeah. So one, it's not all manufacturers, right? I mean, it's really talking about companies that are making very advanced products, advanced materials, things like batteries, semiconductors, etc. And what I meant by that is that manufacturers have an extreme amount of control over what their machines do and an extreme amount of insight and measurements over the environments in which those machines operate. They also have a lot of insight into the performance of the end product. But what they really miss, right, and they have really limited insight into is really the quality of the product as it is being made. So they really miss the moments where, material properties shift and defects formed and yield is lost. So they can see very clearly that when they lose yield or when they have a product that does not meet some spec or does not meet some performance, right? But they
Interesting.
really miss like the actual moments where that occurs.
Got it. So then when we talk about advanced manufacturing in general, before we even get into what you're building, help me understand the landscape a little bit. So when people say advanced manufacturing, what are we actually talking about? Because I think most people, what they hear when they hear that is, they picture something like a car assembly line, right? So, help me understand that.
Yeah, so I think people really think, and even in car assembly line, I think they imagine like a Model T, right? Where
Yes.
it's like it's a bunch of guys with screwdrivers and hammers, kind of
Yeah.
assembling little Lego-like parts, right?
Yeah.
But
Yeah. Yeah.
when I say advanced manufacturing, I'm talking about a variety of products, and those include things like semiconductors, those include batteries, those include jet engines. They even include today's car engines, right? But what is it, a general theme that occurs in almost all what I consider advanced manufacturing, right, is that there are very, very thin and very sensitive layers of different types of materials. And when I
I
say
see.
material, I can mean some metal, I can mean some coating, I can mean some composite of different like tiny bits of material that are some different sort of form factor, right? But really the if you're gonna say like overall theme, what separates manufacturing a hammer from manufacturing something like a battery is that, a hammer, that you see the head of the hammer, you see the handle of the hammer, and that's all there is there, right? Whereas if
Yep.
you look at a battery, even like a battery pack in your, like if you were to look in the back of your Tesla and you were to open and you'd see a big battery pack, well, there's
I mean,
literally
the bottom of
thousands.
your Tesla.
Oh, well, yeah, well, I drive a Honda Civic, so I'm not.
Yeah. So you
So
said thousands.
yeah, but then there's thousands and like literally thousands upon thousands of unique material layers, all with slightly different chemical compositions and slightly different form factors and slightly different thicknesses and densities and porosities, etc.
Yep, got it. So these days, seeing a lot of money flow into reshoring and domestic manufacturing. What's actually driving that, and why does it matter, I wonder, for the kind of manufacturing that you're focused on?
Yeah, so one with that, I think we should like rigorously define reshoring and what that money is actually going into, right?
Yep.
So, for example, a lot of companies right now, big automotive companies, are raising money and claiming that they are reshoring manufacturing and that they are putting manufacturing in America, but really
Yep.
they are literally Chinese companies are putting their employees with Chinese equipment in Chinese plants, and they're just sticking an American company name out front. So,
Yeah.
so I I think one thing to like really understand about this and people really don't get this is like they hear the term reshoring manufacturing and they think America's is magically going to start manufacturing all these things, but like these ecosystems are like way more global and way more interconnected than maybe is obvious to the
Yeah,
average person. But the like general theme over that really is just getting the manufacturing to occur on American soil, right?
yeah,
And
yeah.
why is that important? Well, like one, obviously there's different, geopolitical constraints, right? And we even see recently with actions in the Strait of Hormuz. I mean, I think
Mm.
everyone talks about how that affects like oil prices, but one thing like people don't see is it actually caused like the price of helium gas to like skyrocket, right?
Wow.
And helium gas is like an important industrial gas that is used in a number of things that you would never talk about, right?
Yeah.
So one, there is an incentive just to have some stability against very sort of like unpredictable,
Got it.
geopolitical aspects. And then, second, right, like, manufacturing creates a lot of jobs. And I think again, when people hear manufacturing creates jobs, they think, oh, manufacturing creates, Model T assembly line jobs. No, like manufacturing creates like high paying, sophisticated, stable jobs that can be here for a long time, right?
Yeah, yeah. Yeah, very interesting. Back to the blindness analogy. So I want to try, just so I understand, I want to kind of give you an analogy and you tell me if it captures it, right? So I'm imagining in terms of advanced materials, I'm imagining you're baking a cake, you read the recipe, you put everything in the oven, but you're not allowed to touch it, open it, or check anything inside until it comes out the other end, right?
Yeah.
So whatever happens inside the oven is sort of a black box. So in my mind, this is how materials get made today, but I'm not sure if that's entirely correct. But yeah,
No, I mean
your
that
thoughts.
that's a really good way to summarize it. I mean, and not to, harp on like battery manufacturing, for example, but like, in battery electrode manufacturing, the material will go through a dryer that looks like an oven, and there is no visibility of what's happening to it when it's in that oven. So like that is an exact analogy. Right now, we are being a little, or in the case of turbine blades, turbines will be coated, and
Mm,
then they will go through this testing again, where they're in like a furnace, structure, and they will be tested for like 38 days, right? And like but I would say though, right, like it's not like it's like a closed oven where you can't see anything. You still get some information. Like there are cameras and things like that that exist today, but like if you're baking a cake and you look at the cake and the outside of the cake is cooking okay,
mm,
right? But the inside has some catastrophic area, like you're not going to see that, right? Or maybe what you will see is like you will see the outside of the cake begin to deteriorate, right? But that's only because there was some problem inside it 5 minutes ago that you couldn't see, and now the entire batch is ruined, right?
oh, I see. Interesting. Okay, so then I assume there's a cost to that, right? So what does this blindness actually cost? Like not in abstract terms, but give me an example.
Yeah, so the most legible or like easiest way to imagine this, right, is really a yield loss. And when I say yield, what I mean is the following is if there's a my part becomes bad at step 1 and I do
Mm,
not catch that until step 20, I lose all of the money that I had put into processing this and the extra material I added to it, and extra value I added to that part, from steps 2 to 19, right? So
I
that's
see.
that's one aspect, and that's really what we talk about yield savings. But I think it's very easy to improperly
Mm,
categorize us as purely a yield saving. There's other aspects as well which provide even more values. One that is related to yield, right, is
mm,
not all uncaught errors are of the same cost, right?
interesting.
Well, for example, there's a difference between shipping a low performing battery, where maybe I have an unhappy customer, right, who
Yep.
says, "Oh, why can't my, XYZ car charge as fast as I want it," versus shipping a battery that blows up, and now all of a sudden I have to recall, thousands of cars, and in some cases lose billions of dollars, and there's many well documented cases about that, right? Outside of sort of like yield and safety, there and then there's like yield and safety for like the like types of products you want.
Mm,
But another thing you have to understand is that these manufacturers know that there are going to be certain defects and certain variations that are going to come into their manufacturing process that they have no visibility into and that they have no control over, right? So then they start actually designing the end product to be a little more robust to that, but there's a
Mm.
cost to that. So, for example, people will make battery electrodes about 30% thicker than their ideal performance because
Yep.
they need that extra thickness. They're going to be robust to certain types of defects. So then that also has a certain type of yield loss, right? But even outside of something that I think is really understated is how having extra information about the product that you ship can allow the end operation of that product to be quote unquote better. And better can mean
Mm.
different things depending on your performance metric, right? So, for example, right, an interesting example we were given is that, right now, just to give people background, jet engines are run at temperatures that are above the melting point of their components, right? So right now, like the
Okay.
turbine blades inside of a jet engine, if you just leave them unprotected inside of the jet engine, they would all melt. Okay. So in order to prevent that, these jet engine manufacturers, well, they coat their turbine blades with what are called thermal barrier coatings, right? And just to get
Mm.
into kind of how complex that is, the thermal barrier coating is not like I take a turbine blade and I dip it in something. It's actually like a complex multi-step procedure which involves like a level of surface preparation and then coating and then actually growing a layer on that coating and then actually and then
Growing.
yeah, and then growing and then coating like generally a third layer, right? And really there's no good way to measure the quality of those coatings without destroying the turbine blades. So what do these guys do is they'll destroy like 1% of the blades and then they'll just say, okay, I know there's some variation. I have 1%. I'm going to therefore, assume some big safety margin on the uniformity of those blades.
It's basically spot checking at
Yeah, spot
best.
checking. Yes, yeah, this is spot checking, but they know the 1% they measure is not fully representative of the whole, so to make up for it, they just add some safety margin, whatever. So one of our customers told us that if they just knew the uniformity of every blade, if they just knew the uniformity, there's no change to the manufacturing, there's nothing else, right? They wouldn't have to assume these safety margins, and they could then also even like place their blades in different positions in the end product where they could run their engines up to a certain percentage, like run their engines hotter and
Uh-huh.
therefore more efficiently. So
I
like we
see.
were told for example that if they just had this information, they could run their engines up to 5 points more efficiently, right? And now
Interesting.
and now you think about it too, right? Like, it's not just like jet engines and things, right? So like all of these sort of products, right, especially advanced materials, they exist within some larger architecture.
Mm.
So like a battery exists within, let's take a battery, right? A battery
Yep.
exists in a car. A battery is charge and discharge, right? Right now, there's charging and discharging protocols that are basically averaged over each battery. Well, what if you had more information and you could make custom ones for every single battery, right? Or you can
I
make
see.
custom ways in which the like semiconductors in your computer operate, or et cetera, et cetera, et cetera, right? So like I think people really underestimate how just like the extra information about a product can lead to its like more efficient like end operation. And then finally, this is kind of the last bit here, and I
Mm.
think it's obvious, right? Like if you have more information, you can correct and tune and optimize your manufacturing processes in real time in a better way than you could without that information.
Yep.
So it's like, right, if you see a drift, you can correct it. If you see something about to drift, you can correct it.
Yep.
Ideally, people would be able to do that in an autonomous way, but even with some human in the loop, you can have more effective corrections there.
Got it. Got it. So when I hear turbines, batteries, semiconductors, people have been working on these things for decades. So to me, these aren't necessarily new industries. So I'm wondering, why is this a 2026 problem versus like a 1991 problem?
Yeah, I mean, so, versions of these problems existed in
I see.
1991, right? But, now, like, we live in a world in which the performance requirements are much bigger, right? So,
Mm.
for example, in 1990, the most powerful computers that were the size of a room are as powerful today as like your Apple Watch. So like that necessitates like a different level of complexity, right? Or
Yeah.
these just had to power. They didn't have to power a car, right? So we have like a more complex world. We also have a world that wants to be like less reliant on, fossil fuels and things like that. So we have to,
Oh,
adapt as a result.
interesting. So we got good at making more complex materials, but we still have this blind spot. So we're not as good as seeing what's happening as we're making these materials, right?
Yeah, and and it really is gating us,
Mm,
right? And an example I can give is this, right? Is like the lithium ion battery was discovered. No, we should look that up, but not that long ago, right? I'm gonna Google it right now. It was lithium. I think it's like the 70s, right? Let's look this up. Yeah, 1970s, right? By
okay.
like mid 1980s, like lithium ion batteries were in products, right? They're in like
Yeah.
watches and like little consumer electronics, but where they didn't have to last very long. Okay, the solid state battery was discovered in like the right? And it's still not anywhere, right?
Yeah.
So
Yeah.
it's like, we just are now in this president where we require, we discover much more complex things, right?
Interesting. So these problems are not new. Smart people have been working on measurement, inspection, looking at things, X-ray things, looking at how things are made. Why do you think folks haven't solved this yet?
No, I mean, so let's say solve this, right? I mean,
Yeah.
so like people can see more in line than they could before, right?
Okay.
Right? They just still can't see very much,
What's
right?
the what
And
does inline mean?
yeah, like while like inside the manufacturing line, right?
Okay,
So
so it's
like
a manufacturing line that's moving,
yeah,
and
and
you have okay, got it.
but what I would say traditionally, right, is that measurement to date, the sort of philosophy there has always been, I am going to try to basically have a machine interact with some sample, whatever it is, and
Yeah.
elicit some very, very, very specific signal in some very specific circumstance where I can measure some very specific property. They were never invented in a way or meant to be a way that was like totally wholly generalizable, right? And today they have, traditionally relied on things like cameras and x-rays and ultrasound, and there's been a
Yeah.
lot of developments within cameras and x-rays and ultrasound and lasers. Like all of those things are phenomenally more advanced than they
Mm,
were 30 years ago, right? But even with their advancements, there's just a lot of properties and aspects of these sort of advanced manufacturing products or advanced materials that these tools were not designed to measure, right? Like a camera was never designed to measure the conductivity of a material, right? Like an x-ray was not designed, to
mm.
measure the like chemical composition of something, right?
Got it. So with what we have currently on the market, is it correct to think that there's kind of a physics gap in what we're trying to look at between what
Yeah,
the instruments that we have today and what we're trying to measure in
yeah,
terms of
yeah.
material, in terms of chemical and physical properties, right?
Yeah, for sure. And the other thing that I want to be like clear about, right, is that if I have a product and it's made and I want to destroy that product, I don't care if I
Yeah.
destroy that product and I don't care how long it takes me to measure something. I can measure anything I want. And frankly, to your point too, a lot of advances have really been focused on that. Because like that
Mm,
really is the first step. Right. Like how can I think about measuring something in line if I can't even measure the thing if I'm holding it? I don't care if I destroy it. Right. But
got it.
for sort of being able to like solve this blindness issue, yeah, there's definitely a physics gap
Yeah. So when we're talking about physics, we have to talk about cold atmospheric plasma because that's what you do every day, all day.
every day, all
So,
day.
can you tell me, what that is? And I would love to explain it to me like I'm a person who knows nothing about your product.
Yeah, so yeah, first let's talk about plasma in general, right?
Okay.
So
Yeah.
plasma in general is, occasionally considered the fourth state of matter. It is the most common state of matter in the
Mm,
universe. It's like 98% of the universe is plasma or something. But what plasma is basically a charged gas. So, the sun is a plasma, like all the stars are plasmas.
all right. Cool.
That's what it is. And, when we say cold atmospheric pressure, by cold, we mean a little above room temperature.
I see.
And atmospheric pressure, we mean something that can exist in open air in our atmosphere, not in space. That's like
Okay.
really what we mean, right? So
Got it.
that is cold plasma, right? An example of cold plasma that's like in your everyday life that people don't realize is neon signs are actually cold plasmas.
Neon signs.
Yeah, neon signs are, atmospheric pressure charged versions of neon gas.
Interesting. Cool. So, walk me through maybe an analogy of how you're using this to create maybe like a fifth sense or something like that to
Yeah.
give us information about the world. I'm curious, talk to me a little bit about the sensors that you guys have been developing and all the
Yeah.
technology that you've been working on.
Yeah, so we make, our core product, it's not obvious from how this conversation has gone, is basically a measurement tool, right? There's software along with it, but it's really a measurement tool, right? It's
Got it.
it's sort of core mechanism is that we, expose incident samples like advanced materials, etc., to cold atmospheric plasma. And these plasmas are unique in the sense that when they come into contact with anything, like any material, any sample, they will induce these sort of synergistic chemical, electrical, and thermal plasma material interactions.
Hmm.
So we end up with this scenario where we have this plasma is hitting some material. The material responds to the plasma, and the plasma responds to the material.
Interesting.
And our core thesis there, the entire underlining thesis behind this entire company is that those interactions carry a lot of information. And that,
What type of information?
yeah, I mean, they carry a lot of structural and chemical information about the material. And that if we can record those interactions sufficiently well with specialized, generally off the shelf detectors, right?
Hmm. Hmm.
Then we should be able to translate that information into multiple critical material properties, to performance predictions, to a
Hmm.
variety of, quality control, relevant or process control, relevant, suggestions or classifications, or basically, really any piece of information that is relevant to to the manufacturer or user of that material.
Interesting. So the interaction itself kind of generates data, which you can think of as like multidimensional
Yeah.
signal that somehow maybe records or encodes the material's fingerprint.
That's a really good way to put it, right? I mean, very truly, right? I mean, we are calculating hundreds of thousands of individual signals per millisecond, right?
I see.
And the sort of, combination of those signals really does represent a unique material fingerprint.
So then you have a bunch of data, you can do a bunch of machine learning on it, and then you can do cool stuff, I would imagine.
Yeah, so and this is also where, we want to be, precise, right? Is
Yep.
that, I think, it's very easy to look at this and hear, oh, there's a lot of data and now they just throw some neural network at it or whatever. I'm totally uninterested in that, basically.
Yeah.
Like really, the information that we capture is physical,
I
right?
see.
So really the goal of what we do, and we do rely on machine learning tools or use machine learning tools, but it's really to discover what's going on physically within the
So,
system.
so what does the signal actually tell you? What can you measure that you couldn't measure before, for
Yeah.
example?
So in the context of things like batteries, right? Basically the things we can measure inside the manufacturing line in real time or while the material is being made that previously could not include like simultaneous measurements of things like porosity and adhesion, and things like chemical composition, conductivity. We can
Interesting.
identify the presence of sub 30 micron size metallic contaminants in the bulk of electrode materials. We can find special defects on the edge of those electrode materials, find special pinhole defects within them. And, right now, the only thing that can be found inside those lines is just the thickness of the material. And it actually can only be found on single-sided electrodes. The whole industry is going towards double-sided. That's a different conversation. It we yeah, I think those are good examples of things we can find
Hmm.
in lab that no one
Interesting.
else can measure.
Yeah. So back to, going from maybe this idea of measurement to the idea of intelligence, right? I want to ask about the
Yeah.
phrase that you've been using, measuring intelligence, because I think people hearing this for the first time, I think we're just describing like a better measurement device. So
Totally.
what's the difference between like call it a smart sensor and a manufacturing intelligence platform?
Yeah, so let's think of like a very famous sensor, like a very famous, well-known sensor is like what's called ellipsometer. It measures
An
thickness of
ellipsometer?
ellipsometer, man. It measures thicknesses of, bunch of different materials, but it's very commonly used in semiconductor, right? I mean, the one of the fundamental outputs of that is just outputs the thickness of the material, right?
Okay.
And you use the thickness, you know how thick it is, and that's what you know, right? But there's nothing else that can be used later, right? Whereas, for us, right, the first level output is really this material fingerprint, right? And at a first level, yes, we can get things like, different properties like thickness and density and conductivity and etc. And that is valuable in that moment, right? But the, only part of the fingerprint is used to sort of output those properties, right?
I see.
Now, what's interesting about it is like you can then store that fingerprint and look at that fingerprint, something that I think is particularly attractive, to our customers. And we say, look, you have this entirely novel class of raw data. You can store this data for 6 months and then correlate that data to downstream like end product performance in the field. And after 6 months, to sell there's something new about your manufacturing process or your product that you didn't know before, right? So it's like really the fact that this same level of raw data can be used, one level for like property prediction, can be used on like a second level, like, a little less immediately for like some broader, process intelligence, right? Like how, what is something new about my product or my process or my manufacturing equipment or whatever, and then can be used at a fourth layer as like it'll actually like optimizing and changing the manufacturing process in real time.
Interesting. Got it. So instead of you hitting start, recipe happens, you look at the end, you now have kind of a continuous understanding of what's happening.
Yeah, and it's really meant to, right, to increase the manufacturer's understanding m- of their processes over time, right? And I think that's one thing that's in general understated about manufacturing. I mean, I think people think, oh, if I build a factory once and I have all this equipment and the factory is running pretty well, I can just copy that factory to a new location. And the fact is, like, that copying process is actually really complicated, right? Like, even places like CATL, like, very famously, like, sometimes it takes them like 2 years to copy a factory, right? Right, and it's because, like, there is so much information in how the process is run, and a lot of that information is, like, legacy, a lot of that is not particularly well understood. A lot of that, like, anyone who works in any advanced manufacturing process or any advanced product development can tell you some anecdotal story about how some seemingly arbitrary change in their process made a huge difference, right? And is that because the process is magic or that change is magic? No, it's because there's a lot of things that are not understood, right? And so the more you can allow manufacturers to understand their process, have visibility into their processes, like the more valuable you are, the quicker they can copy it, the more money they can make, the faster they can go to market, the more they can be robust against certain types of environmental or other changes that they can't predict, right?
Super, super interesting. So it's fragmented. You have these local optimizations that are happening by engineering teams, right?
Yeah.
And then each engineering team, they know, okay, this is my process. This is how I run it. These are the values that I need to input in the control system. And I just know that you don't change it and it works, right?
No, but but hold on. That's the thing is like there also are little micro changes, right? And a lot of times those are actually made by like the technician who isn't necessarily communicating that to the engineer,
But he's been
right?
there for 15 years.
Yeah, but he's been there for 15 years, right? I mean, there are stories, right? I've never seen this, I know it's true, but there are stories of like, technicians at big battery manufacturers like literally sticking their fingers in like the slurry used to make electrodes and tasting it. And like based on that taste, making certain and what's probably true is they probably can't articulate like, taste leads to something better or not, but they know that the taste correlates to some different operation parameter, right? But like
Yeah. Yeah.
it's like I think people imagine manufacturing is like these parameters are constantly just locked in. Like you lock in these parameters all of a sudden. It's not true. There are little changes every day. Like the scale of those changes are smaller than like when you're bringing something up and you're changing things much more drastically. But like certain change and adjustments exist, right? And they're not always communicated. And a lot of times it's from technicians, and there's just very incomplete information, right?
Yeah. I would imagine even by hearing the equipment, they can probably tell
Yeah, I
if
mean,
it's
yeah,
like,
who knows? The interesting podcast would really be to, find all the 20-year plus experienced technicians and ask them and ask them how they want run their processes, and then ask maybe, a technical manager 3 levels up and see what the discrepancies are, right? And
oh my
and
God.
you and you can see how that can matter. And let's say something like semiconductor, we have some 3 nanometer node, how the smallest change can matter, or some battery, right? But if you're manufacturing like a hammer or a Model T, like if I'm putting a hammer together, does it matter if I slam it together? Does it matter if I like, put it together softly? Does it matter if I drop it? Does it matter, right? All these
Interesting.
things.
Fascinating. Cool, man. So back to manufacturing as a whole, I think there's a lot of AI hype right now. You got digital twins, predictive
Yeah.
maintenance, autonomous this, that, and the other. Where does your company SirenOpt fit into that picture? Are you competing with that? Are you enabling it? How are you thinking about it? I would love to hear your thoughts.
Yeah, I think a big value of what we do are enabling things like
Mm,
digital twins. And like, first of all, let's be very precise about what the term digital twin means. I mean, people say digital twin, and I think they literally think it's like a digital copy of the factory, right? A
yeah,
digital twin is a model. It's a model. You can pair visualizations with it, right? But it's a model that has inputs and outputs that mirror or approximate what's going on in the real world in some capacity, right? You can imagine that those models are better if you have more data, more visibility into the process, etc. Right? So
interesting.
we certainly enable those, right? But one big difference and one big advantage that we have is, I think it's very common to, and the term digital twin I think is very overused, but when people talk about digital twins, a lot of times they talk about adding more data, and like really what a
Yeah,
lot of times what that means is like they will take a lot of different just sort of telemetry data, like what's the environment like, let's take pictures with cameras, let's log like where certain humans are, etc. And they will try to like correlate that data in some purely data-driven way to some output, right? And they'll
interesting.
throw a big neural network at it and they'll say, look, this is predictive. What is fundamentally different about this is like the data that we collect is inherently physics grounded.
Hmm, hmm,
And because it's inherently physics grounded, it is meant to extrapolate, right? Or to be like really interpolate, like sort of beyond that reach, right? So certainly I view this as enabling things like digital twins, certainly I view this as enabling autonomous factory, etc. But another point I want to make is that some aspects of that software, like particularly the aspects of like real-time process control software, we do want to write. We are uniquely suited to write. Another thing that I think is understated, right? When people talk about autonomous factories and they talk about machine learning solutions, I think people really imagine there's going to be some supermodel, like some chat GPT that just makes every factory autonomous, right?
yeah, yeah, yeah.
But like really anyone who works in these knows that, these models are best when they are tailored for scenarios, right?
Yep.
And so in order to really use our data, well, you're going to have to really understand our data very well. And so like we also plan to create real-time process control software and are creating various types of decision-making software, and we're uniquely suited to do that due to the domain knowledge we have about this raw data.
Interesting. So let's dig a little bit deeper. Maybe we talk a little bit about who's
Mm.
actually using this today. I'm not sure if you can mention some of your customer names, but these are, not companies that run experiments for fun, right? I'm curious, what
Yeah.
does it mean that they are in the deployment with you? And if you can, it'd be great if you could mention like some of your customers.
Yeah, I mean, yeah, the only customer we can really mention publicly is one that invested in us, which is which is Jaguar Land Rover, right?
Which is who?
But Jaguar Land Rover, which is a subsidiary of Tata, right? But I mean, what I'll say is like, we have customers who are real deal tier one manufacturers, right?
Yep.
And the internal champions we have for these customers, and I'm thinking one case in particular is someone who has led this customer's non-destructive testing for 20 years, right?
Hmm.
Like these are people who really have seen every single tool there is to see, right?
I
And,
see.
from an aspect of testing, I mean, I think it's important to talk about like, how we first engage with customers, right?
Hmm.
And, the fact is we are the first people to ever use cold plasma for measurement. There is a
Hmm.
novelty aspect there. I
Hmm.
think customers and scientists in general should rightly question the like validity of that and say that is weird. I've never heard of that. I don't understand that. Like we need to test it, and we'll always say yes, right? But like I say this to say that the sort of understated cost here, right, is the amount of validation the customer has to do, right? So
Hmm.
and so a class example I'll give is like the first way we interact with customers is that we will, they will, send us some samples that we'll measure, and we'll send them back to like verify the measurements.
Hmm.
And sometimes those customers will spend 4 months verifying those measurements with 6 different instruments and using each instrument to like measure each material multiple times, right? But then once they have that confidence, then they will really go. Right?
I see.
So, there's like what it means in each case is like your customer, yeah, they have to prove some budget to pay us, fine, but they also have to, really make the arrangements for like their team and other teams to have the time and testing and,
I see.
evaluation capabilities to really see if this is real or like how it can be useful for them. And we've really had no, we have had I would say a lot of success getting these evaluations and participating in very in-depth evaluations and moving more, obviously to more serious commercial engagements as well.
Interesting. So they send a sample. It could be a battery or one part of a turbine blade, or even like one full turbine blade, and you'll run it through your process and give them a data set, and then they take that sample back and they cut it, they measure it, they use cameras, all those things. So you do something maybe in a few hours, send them the data, and then it takes them that much longer to just to confirm that the data that you sent them is correct.
Yeah, I mean, and sometimes too, there's an interest on their part where like these customers very clearly see that, the real cool value is that we have this novel class of raw data, and they very much know that there's things that because they have more expertise about their materials than us, that they can use our data to see.
Interesting.
An example I'll give is that and a lot of our best customers are, Alice, forgot where I was going. But, one example I'll give is one customer, we, like, ran a little POC, and it was really in the context of measuring some property on their
Yeah.
separator coatings, right? And,
Uh,
obviously, they're gonna take time to validate that, fine. But what was separate than that is they actually took the time to, like, look through our, like, thousands of, like, raw data signals, and then actually realized that, like, some of our raw data actually indicated that, we could really determine like the anisotropy of pores in their separator coatings, which is a big problem for them, but nothing that they ever, eh, you know,
So they didn't
verbalize.
even think to measure
Yeah,
for
yeah,
that
yeah, yeah,
or to
yeah,
test
yeah,
for that or look at that.
yeah, because they're like they didn't think there was any way this tool could, our tool with their limited knowledge could potentially be capable of that, right?
Interesting.
And that, but even this sending, our samples, I mean that is a first level of evaluation, and then there's second levels which involve us deploying tools, and just to be clear, our tools are running at multiple tier one manufacturing sites in North America, Europe, and
Yeah.
Asia right now, right? So
All right. So how do you make money? Right, so on the surface, it sounds like an awesome idea. Cool.
yeah.
Maybe even it sounds like a hardware company at the service. But I suspect the story is more interesting. So yeah, how do you kind of make money?
Yeah, so we sell the hardware,
Uh huh.
right? So we like sell the hardware for a CapEx acquisition fee, right? Now all advanced manufacturing equipment, advanced, measurement equipment will always be, a hardware sale and then a 10-year annual support fee for the lifetime of the tool.
10-year. That's what the industry standard is.
10 years, man.
Wow.
Over the
Very
over the
cool.
over the 10-year lifetime of the tool. So there really is, you can look at it as like a 10-year annualized value, but it's really upfront CapEx acquisition fee and then support. And then on top of that, we sell software, right? And the sort of kind of core modules there are really, the OS used to operate the tool and to do
Hmm.
sort of model predictions and things like that. Then there really is an analytics suite, right? Which is meant for really looking at all this raw data, analyzing and finding patterns and correlating to various, operation parameters, etc. And then
Yeah.
there's, we call it like the analytics module, right? And then we have a sort of, fourth level here, which is really a process control module, right? Which
Hmm.
is the real decision making module, right? Because there is a fundamental, there's obviously a leap, right, between hey, these are the correlations between X, Y, and Z or A, B, and C inputs, etc. Versus
Yeah.
okay, now we recommend you change this or let us change this automatically.
Interesting. Cool. So walk me through high level economics. Let's say I'm a turbine manufacturer. I write you a check. What happens to my P&L line?
Yeah, so in the case of turbines, right, in immediate the most immediate value add really is the fact that, and let's just take turbine blades for example, right? Is
Yeah.
turbine blades are actually very highly regulated industries,
Mm.
right? So like you really legally cannot ship poorly coated materials, right? And so what happens is, you go from bare substrate to coating, you test it at the end and it's not very good. And then you go, no way, now I have to strip this to the bottom and recoat it, right? So in the immediate term, you can test each layer so your throughput will improve, right? In addition, right, you will catch catastrophic errors earlier. And again, that prevents you from adding, layers to poorly coated or poorly manufactured materials. So you will see a
Mm.
yield improvement. Yield and throughput are related there. And then, in a sort of, I guess, less immediate
Mm.
term,
Mm.
You'll have more information about your turbines so you can operate them more effectively. And
Yeah.
then in a longer term, you will have a totally new class of information to describe your entire manufacturing process, which will allow you to make, ideally, like really truly transformational process changes.
Mm. Mm. Okay. How do I think about ROI in this case?
Yeah, I mean, ROI, I mean, I think you should think about one, a yield and throughput improvement, right? And
Yeah.
then with that also, I mentioned, destructive testing is a huge part of this, right? You
Yeah.
should just destroy less samples for testing.
Yeah. Yeah.
So there's that. And second, you should think of a performance improvement in terms of the operation of the end product, right? And the
I see.
ROI there is you have a higher performing product, you should be able to sell it for more or sell more of them or
Yeah.
take more market share, right?
Yeah.
Then you should think about the fact that you have more information to optimize your processes,
I
right?
see.
So now in addition to operating the end product in a better way, the end product itself is actually better, right? Uh
Interesting.
and video, this is also understated. You also have like extra guards against like catastrophic errors, right? Like even turbine blades, like I said, you legally can't ship things that are poorly coated or whatever, but you also can't test every single component,
Yeah.
right? So like slip through, right?
Yeah.
And these companies do pay they're paying hundreds of millions of dollars in insurance payouts and liabilities, etc., right?
Yeah.
Due to undetected defects and contaminants, right? So you also have just an extra security against that. Right.
Yeah. Very good. Interesting. Cool. So then one comparison that I've been hearing people say when they mention your company, which I'm not sure it's correct or not, but they sometimes refer to KLA in semiconductors, right? This is a company worth 200 billion that essentially, I think, owns the measurement intelligence layer for chip manufacturing. Is that kind of the right analogy for SirenOpt? Or can SirenOpt get that big? How should I think about that?
Yeah, I mean, I don't know if I consider KLA like a measurement, like an intelligence company. I mean, I think
I
they do
see.
classic metrology and measurements. They are really good at measuring individual properties well,
Okay.
right? But they can do it really well, right? Right, and they can do it for, very expensive tools, etcetera, right? I mean, I really think that, you know, a comparison for us to KLA is fair at the initial sort of property prediction level, but their tools inherently do not lend themselves to these additional layers of value via these sort of, analytics and process control type software, which
Interesting.
is why KLA base doesn't sell any software, which is
Yeah.
why Keyence doesn't basically sell any software. I mean,
Yeah.
so Applied Materials doesn't really sell any software, right? Lam doesn't sell any software. I mean, I'm sure they make some, but, right?
Interesting.
Right. So yeah, right. I really think the more appropriate analogy in a lot of cases, like, really is these sort of other types of kind of manufacturing intelligence companies, right?
Hmm.
Which
Hmm.
maybe are not focused on advanced manufacturing, but maybe are focused on maybe just in general, like just intelligence companies, which are
Yeah.
collecting multiple modes of data to have a new raw data layer that can be used for a bunch of things.
Interesting. Okay, so let's talk a little bit about competition. This seems to be kind of a clear opportunity, right? You should be looking at how to improve these yields. Everybody should be avoiding catastrophic failures and all these things. But why isn't like a well-funded incumbent building this, right? What actually kind of makes Siren up unique in terms of competition?
Yeah, I mean, so people are trying to build better measurement tools,
Mm.
right? But certainly, right? But like I would say our really unique aspect is the fact that we use cold plasma and the
Yep.
fact that that allows for this multimodal sort of inline non-destructive measurement, which really like there really is, like you said earlier, a physics gap which the world
Mm.
has never seen, right? So I
Mm.
think a fair question is like, why has no one else used cold plasma for measurement,
I,
right?
that's a
Right.
better question. I see.
Right, and I would say there's sort of 2 things. Well, one, I co-founded this company with my former PhD advisor based on the research I did my PhD at UC Berkeley. And, you know, really the first thing that we were trying to do, like, we were not trying to make a cold plasma-based sensor, right? We were actually trying to control cold plasma for, biomedical applications, right? And we were the first lab ever to apply machine learning in any capacity to cold plasmas. We're the first people in any capacity to try to control cold plasmas, right? And why is that? Why is that control important? Because it allows us to have a consistent measurement. And just
I
really
see.
nobody had tried to do that. I mean, in a very serious way. And like part of the reason for that is like in order to do that, you need to rely on some machine learning techniques which weren't around, 20 years ago, right? I mean, that is
Interesting.
part of it, right? Uh, uh, and then, a second reason for that is like outside of plasma control, a huge part of this really is, well, translating the plasma material interactions into useful information, which again relies on a physics informed machine learning component, which those types of techniques again were not around a long time ago. Right? And then the third is like, even if you wanted to remake this,
Mm.
right? And hey, look, if you put 20,000 people on any problem, they could probably solve it, right? Right. But even if someone could copy our box today, right? Like there is something that's extremely critical to the performance of the tool is like actually the amount of data that we've collected and that is used in not only the operation of the tool, and there's a huge space of potential ways to operate this, right? But also in like how our sort of models and control algorithms and sort of different prediction works. So there would just be, even if someone would kind of say, there's still a huge time sink, and you have to measure a lot of materials from a lot of different companies and like, from a lot of different labs or, et cetera, to like really learn about your tool, right?
Yeah, interesting. So I know you and Ali, your co-founder, created the technology at UC Berkeley. At what point, I wonder, you looked at the research and say to yourself, this could be a company, not just kind of like a research paper?
Yeah, I mean, so the full story here is we were really developing these cold plasma systems for a different application. Over the course of that research, we basically accidentally realized that this system could be repurposed as a measurement tool or as a sensor, right?
Interesting. Okay.
But at that moment, we very immediately realized this could be a company because of our other research, we were very intimately familiar with, advanced materials manufacturing, advanced manufacturing in general, and like, how much limited visibility into manufacturing lines affects how those lines are controlled. So there was never really a time where we thought this would be a paper, because even inventing like a new product like really isn't a research paper.
Interesting. Cool, man. So where can people learn more about SirenOpt?
They can go to our website, www.SirenOpt.com. We also did just give a talk at the Volta Foundation this morning, presenting interesting results that we had collected with a collaborator that, shows that we can measure multiple critical material properties of various battery electrodes.
I'll put that link in the show notes. But awesome. Really good to have you on, man. Thank you so much for your time today.